So usually when people think about a continuous function, they think of somebody saying, oh, well, a function is continuous, as if when you draw it with some sort of pencil on the graph, then your pencil doesn't have to move while you trace it. Now, and that's kind of a intuitive understanding of continuity, but the more rigorous definition is that a function is considered continuous if the value of the function at the point is the limit of the function at that point, is the limit of the function at that point. So really what am I trying to say is that, if f is continuous at 3, if f of 3 is the limit of f as x approaches 3, right? So the idea is you end up where you think you're going. That's kind of an idea behind continuity. And for vector valued functions, we have the same idea. It basically says that if I have a vector valued function at some number, when I plug in that number, if the limit approaches that number, then I can be reasonably confident that, or not reasonably confident, I can guarantee that it's continuous at that point. But generally, continuity at a point isn't that useful. We want to think about continuity on an interval. Ideally, the interval is huge, just a bunch of values. But what we say is that it's continuous on an interval if every value in the interval r approaches. So an example of that might be if this is a vector valued function in the plane, not necessarily in space, then we would say that r is continuous in these open intervals, not necessarily the closed ones, so they don't include the endpoints. It's not continuous here because as it approaches, the actual function value is down here. So you think you're going this way, but you end up over here. So the function's not continuous here, but everywhere along this interval and everywhere along this interval, the function actually is continuous in those intervals.